Hello everyone, in this video I would like to do with you an exercise on contiguous memory allocation. And let's suppose we have a system equipped with 512 megabytes of RAM where process allocation is handled following a variable contiguous partition scheme. And we need to know that the OS is resident permanently in the first RAM section of 128 megabytes. The process table, and I already wrote the process table of the active processes that are already in memory, contains for each active process the starting address of the partition and the sides of the partition. And memory partitions are allocated with worst fit strategy, and free partitions are handled using a free list, which is a linked list of free partitions sorted by decreasing sides. And this will help us when we want to allocate another process because we will choose the one with the greater sides. And in this free partition list, each list node has two fields, a pointer to the next partition, exactly as for the process in the process table, and the sides of the free partition that we have, both represented of 4 bytes, exactly as in our process table. So, first of all, I would like to have a visual representation of the memory. So, with all addresses and the space occupied by the OS and the active processes and the free blocks that we have. And we will calculate the free list. So let's represent our RAM memory as a block like this. This is our RAM, where we have a starting address of 0. So I will write 8 zeros because the representation is on 4 bytes. And we would like to know the very last address of our RAM. To calculate it, we simply need to convert this number, 512 megabytes, into hexadecimal. So we want 512 megabytes, which is in decimal, in hexadecimal. Let's find out a way to do it manually and in a simple way. So first of all, I'm converting 512 in hexadecimal by dividing by 16. This is equal to 32 with a remainder of 0. So then I'm dividing 32 by 16, which is exactly 2 with a remainder of 0. And in the end, 2 divided by 16, which is exactly to 0 with a remainder of 2. So my number 512 in decimal is going to be 200 in hexadecimal. Okay, so here we have 200 megabytes in hexadecimal. We would like the representation of hexadecimal number as this one, and in order to do that, it is important to recall that if I have 1 megabyte, this is 1 multiplied by 2 at the power of 20 bytes. All right, and in the binary representation, this is exactly some zeros, a 1, which is this one, and this one is followed exactly by 20 zeros. All right, and why I'm saying this? Because the conversion between binary to hexadecimal is particularly easy to do, because 4 bits in binary can be converted directly in hexadecimal, and they will be exactly 1 bit. So 4 zeros in binary will correspond exactly to 1 0 in hexadecimal. So this means that if we have megabytes here, we simply add 20 divided by 4 equal to 5 zeros after this number that we have here. Okay, so this number here, 200, sorry, megabytes in hexadecimal is going to be exactly the address 0, followed by 2, and so 200, sorry, followed by 5 zeros. All right, and we see that we have exactly 8 bits, so it is correctly represented on 4 bytes, and we can say here that our last address is 2 followed by 7 zeros. All right. The second thing that we know is that the OS is occupying the first 128 megabytes of the memory. So the OS will start here and it will arrive at some point in the memory where we have these sides, which is 128 megabytes. We have to do the same exact thing to calculate the very last address of the OS that we did to calculate this address here. So let's convert this number 128 megabytes from decimal to hexadecimal. I'm doing the same steps, so 128 divided by 16, which is exactly, just a moment, it should be 8 with a remainder of 0, and then I'm doing 8 divided by 16, which is exactly 0 with a remainder of 8. So my 128 in decimal is going to be 80 in hexadecimal. Sorry, hex. All right, so here I have 80 megabytes in hexadecimal. So what does this mean? This means that I have 8 0 followed by 5 zeros because of the megabytes. Did I add? I add one more. Okay, so 2, 4, 5. These are only 7. I need one more, so I will add a 0, and this is my representation in hexadecimal of 80 megabytes. So this address here is going to be 8080. All right, then followed by zeros to arrive to have 8 bits. All right, then we know that we have a process P10 and a process P11. I want to know where are they in the memory, where there is free space in the memory, and to know everything about the partitions that we have, the occupied one by the processes and the free one. The free ones. So let me just write that our OS have a starting address at 0, 8 zeros, and have a size exactly of 0x080000. Okay, so let's try to place our processes somewhere into memory. We know that the first process, which is the bigger one, starts at this address, and the second process starts at this other address. Of course, this one comes before this one, so for sure it will be something somewhere like this. We will have a process like P10, and the process P11 is going to be somewhere like something like this. All right, so we want to know the So this one is P10. We want to know, we of course know the starting address, so this one is 01. And we don't know the ending address, but we know the size of it, which is this one. So 0A. And here there will gonna be a free block. Okay, we want to know the size of it, so it's the very first thing that we're going to calculate. And then here we will have another possibly free block, since the address of P11, which is here, let's suppose, so 0, 1, 7, 8, etc. And here starts P11. Let's draw it a little smaller than the P10. And we don't know where it lasts, but we know the size of it, which is 088. All right. So in order to have the free list, we need to know information about this free block, and then we will order them, and this other one eventually, and we will order them by decreasing order, but we need to know all the information about them. Okay, so let's start to calculate the information of the very first block. Let's call it F1. We know the first address, so the starting address. So for F1, I could already write the starting address, which is 08. Okay, and we need to know the size. How can I calculate the size? Of course, I know the last address of this partition and the first address. So I will simply subtract from this number this other number, and just be careful with these operations that we are going to do, because they are done in hexadecimal. So I have 1, 0, 0, and a lot of zeros, minus 0, 8, 0, and a lot of zeros. So here we have 0, 0 minus 0 is 0, 0 minus 8, I cannot do it, so I'm taking this information here. 16 minus 8 is equal exactly to 8, because we're doing the operation, I remember you, in hexadecimal, and 0 minus 0 is going to be 0. So the size of this free partition is exactly as the starting address, which is 0, 0, 8, and then all the necessary zeros. All right, so let's do the same for the second partition, free partition. I can call it F2. What do I know about this partition? I actually know the last address, but I don't know the sides. No, I don't know the this address here and the sides, right? How can we do that? We should calculate this address by adding to this address these sides here. Okay, so for F2 we are calculating the starting address by adding to 0, 1, etc. the sides of the process P10, which is 00A. So here it's very easy because it's 1 0 A 0 0 0. So the starting address for the process F, for the free partition F2 is going to be 0 1 0 A 0 0 0 0. And the sides, to calculate the sides, we are simply subtracting as before the last address to the last address, the first address of the partition. So I'm going to do 178 0 0 0 minus this starting address here, so 0 1 0 A 0 0 0. So here we have a lot of zeros, and we have to do 8 minus A. A in hexadecimal is 10, so I cannot do this. I have to steal something from this other position, and here I will have 16 plus 8, which is equal to 24. So I'm doing 24 minus 10, so it is 4. 6 minus 0 is 6, and 1 minus 1 is 0. So the sides of this F2 block is going to be 0, 64. All right. I still have to calculate the information of the very last free block. Let's call it F3. And in order to do so, I would like to know the very first address, quindi for F3, the starting address. I'm going to calculate it by adding to this address here the sides of the process P11. So the address here is 0, 178, followed by a lot of zeros, and the sides is 0, 88. So here we have zeros. 8 plus 8 is equal to 16. So I will have 0 with a carry of 1. And here again I have 16. So 0 with a carry of 1. 1 plus 1 is 2. And this is the very last, the first address of F3. But let's notice that we calculated before the very last address of the memory, so we actually don't have any free space after the process P11. So this F3 here doesn't exist. So what I can do is say that this is whole P11. It's not really representative of the memory because this one is smaller than this one, but anyways, this is a visual representation. We found out later that there was no free space after P11. All right, so our free list is going to be made up of these two nodes. We have to order them by decreasing sides, and so first the bigger one, which is this one, because 8 is greater than 6. So our free list is going to be made of this node and this other node. right? I did a slightly better representation of what we have found out until now. And so to summarize, we have in the very first part the OS from this address to this address. Then we have, then we have a free block from this address to this address. We have the process P10, then another free block, and then our process P11. And these are the partitions that we have. So for the OS, our free list and our P10 and our P11. Now we would like to add a new process. So a new process, let's call it P12, is started. And it requires 25, so the size is 25 megabytes. So we have to allocate it. And since we're using the worst fit strategy, we will allocate it somewhere like here, P12. And so we want to know the new partitions of the memory. So we want to calculate the informations for P12 and the new free list because it is going to be modified. So let's start with the informations about P12. We know that the starting address is this one. So I am already writing it down. So 0, 8, 0, 0, 0, 0, 0, 0. And we know the sides. We know it, but it's in decimal. So we want to convert it into hexadecimal. So we're doing the same steps that we did in the beginning. So let's convert 25 by dividing by 16, which is 1, with a remainder of 9. And then I'm dividing 1 by 16, which is 0, with a remainder of 0, with 1, sorry. And so 25 in decimal is 19 in hexadecimal. We are having again megabytes, so our representation in this other version of hexadecimal is going to be 19 5 zeros and 5 plus 2 it's 7. We're missing 1 0, which we are adding, and this is the sides of our partition. We can write it here. All right, so let's now find the informations for our free block here. We don't know the starting address, and we also don't know the sides. Okay, so to calculate the starting address, I am adding to this address here the sides of P2. So for our free block, I'm calculating the starting address. I say it by adding to this number here the sides of P12. So I'm adding 0, 19, etc., etc. So here I have 0, 0, 0. And here I have to do 0 plus 9, which is 9, 8 plus 1, which is 9, and 0. So this is my my first starting address of this partition. So it will be 0, 99, and then all the necessary zeros. I still need to calculate the sides of this block. To do so, I could subtract from this last address of the block the address that I calculated right now. So I'm doing 1 0 0 0 minus 0 9 9, and then all zeros here. So here we will have zeros, and here I need to do this. So in order to do this, I cannot do 0 minus 9. I remember that I'm doing a hexadecimal operation. So I'm stealing from this one. Here remains 0. Here I have 16. So I need to do this. And now 16 minus 9 is equal to 7. 15 minus 9 is equal to 6. 0 minus 0 is equal to 0. So the sides of this free block is going to be 0, 67, and all the necessary zeros. All right. So the configuration now of my partitions is slightly modified, and I'm going to update them. So for sure the OS remains the same. In the free list we don't have this anymore. So I'm deleting it, and I have this other block which has this size which is smaller than this one. So this one is going to be here, and the second node is going to be after that. So I'm just copying this information of the free block. With the sides 6 7 0 0 0 0. Right, so p1 0 and p1 1 will stay the same, but I will have also p1 2 with this information that I calculated here. So with starting address 0 8 0 0 0 0 0 and a size of 0 19. All right, so we added a new process in our environment, in our RAM. Okay, hope this could be useful for someone. Thank you for watching the video.